Okay, in this video, we're going to answer a sample problem for our lesson in adjustment of stresses. So, the sample problem goes, a repetitive beam member with a span of 3 meters carries total uniform and concentrated dead and live loads as shown. The beam is a 3-inch by 4-inch dressed lumber made of Alaska cedar number 2 grade. The beam is exposed to weather, and it can be assumed that the beam is under moist service condition. Since the beam is exposed to weather, it will also be assumed that incision is done for the application of treatment preservative, assuming normal temperature and edgewise loading. Determine the allowable bending, shear, and bending stress. I already list down the given. So it is a repetitive member, Alaska cedar number 2, exposed to weather and moist, and then there's an incision. The size is 2.5 by 3.5 as indicated, but we can also look at that in our table. So we have here our table for section properties of standard rest sawn lumber. Since it is nominally 3-inch by 4-inch, there, it's a nominal size, and then we can find the standard rest size to be 2.5-inch by 3.5-inch. Okay. Then we are required to find the adjusted stresses for bending, shear, and then bearing. For bearing, I used the notation F prime C P because I cannot make the perpendicular symbol here. We'll go over the adjustment factors one by one. So first, let's first compute for the load duration factor CD. And then since our loading types include dead load and live load, so we have here our options, either 0.9 or 1. But as we have discussed in the previous video, the shorter duration will govern, or simply the higher load duration factor, which is 1. So CD equals 1. That would be for FBA, FV already. Okay. Next is size factor. First, we have to determine if this is a dimension number or is it a timber. Remember the criteria. If the thickness is 2 to 4 inches, then that's a dimension number. And the thickness is nominally 3-inch. Therefore, it is indeed a dimension lumber. So let's get over the size factor. The grade is number 2. So we'll use this area here. And then the size, for the size here, you should consider this as the nominal sizes. Obviously, you cannot see any decimal in there. So that's nominal. Okay, so again, the nominal size is 3 by 4. So 3 by 4, which is our CF for FB is 1.5. I'll just use this notation, CF for the size and then FB as a specific for the bending. So 1.5. And then we're also, okay, so no need to look for the size factor in tension and compression because we're only required to get the adjusted stresses for shear and for bending, shear, and bearing. Okay. Next is the moisture factor. So for the moisture factor, we need to determine if it is dry or moist. Well, it is explicitly stated that the member is moist, and therefore we will not be using this table, but rather this one. For moisture content greater than 19%, then we use table 3b. And then since it is a dimensional number, then we'll use this part here. But for bending, we need to determine first the quantity FB times CF. But we don't have yet the reference design value. So maybe let's get first the required design values. Okay, so we will be using table 4A. As we have stated earlier, it is a dimension number. And then Alaska Cedar number 2. So Alaska Cedar number 2. And then our FB is 800. Just list it here. The unit is PSI. Here you can see. And then FV for shear is 165. Okay. And then next, for FCP, well, it's all 525. Okay, so going back to the moisture factor, we need to get the quantity FB times CF. So we already have CF. Times FB equals 1200 PSI. I'll just note here it is for moisture. And then, since it is 1200 PSI, then that's greater than 1150. Therefore, if it is greater than, we will not use this condition, we will use the original one. So Cm for FD is 0.85. The next, for FV, 0.97. Cm FV was 0.97. Then for FCP, 0.67. Okay, next. Temperature factor. Since nothing is said of the temperature conditions, we have to assume that normal temperature conditions occur. So this, we will consider this column here, less than or equal to 38 degrees Celsius. But it's already mentioned that the moisture condition is wet, and therefore we will use this one here. But in any case, it's all CT equals 1. Okay? Next. Repetitive, yes it is. So that was already mentioned. And the next is the flat use factor. And it was mentioned that edgewise loading. So that means this one, strong axis bending. Therefore, CFU equals 1. Next. Incision. It was mentioned that incision is done, but no specifications were mentioned. We have to assume that this provision is already satisfied because I have mentioned in the previous video, if these provisions are not satisfied, but an incision is done, then the member cannot be used anymore. So for us to be able to still use the member, we have to assume that these provisions are satisfied. And therefore, the incision factor will be 0.8 for bending and shear. And then for bearing or C perpendicular, 1. Next is the bearing area factor CB. Well, from the member itself, you can observe that the supports are not interior supports. So as I have mentioned in the previous video, I've emphasized that this only applies to interior supports. Therefore, CB must be equal to 1, or there is no adjustment at all. Now here in the sample problem, whenever the factor is equal to 1, I still explicitly write it. But in your excerpt, you can choose not to write it at all because if it is 1, then that just means that there's no adjustment needed. Let me just correct this. Load duration factor. And then size. Okay. So after all those, the next is beam stability factor, but as I've mentioned, we'll tackle this in the next chapter. For now, we'll just assume that this is 1. Okay? I put a note here. It has to be assumed for now only. Next, we'll apply the adjustment factors. Okay, so for FB, the adjusted is equal to CB times CM for FB. I think I've put it there, right? And then times CF for FB times see if